Let me open the slides. Neural networks. Okay. All right, let's see. How do I share screen? Share. Okay. So this is a neural network. Can you see the slides?
Yes, yes.
Okay, great. So this is how what the neural network looks like. Basically, you have a set of layers, and so this is the input layer. So you have a set of features. Yeah, this is x1 till xd, and you have the one which is the additional artificial feature that we've added for the threshold. And then you have multiple hidden layers. So we have here two hidden layers, which consists of a set of neurons. So these thetas, right, circles with thetas inside, are called neurons. And they act as if they are perceptrons. So you have here, the first hidden layer has 3 neurons, the second hidden layer has 2 neurons, and the output layer has just 1 neuron. So the lines, the blue lines represent weight. So every line, every edge in this network has a weight. So Wi, J of L, where L is the layer, I is the input, and J is the output. So this is going to be W0, because it's coming from right input 0 to neuron 1. So W01 of layer 1. Yeah, this guy, the red one here, is W2 and 2 of layer 2. Yeah, so this is how it is referenced. So now the idea is the following. I want to find these weights, the weights on these edges, the blue edges, the red edges, the green ones, and so on. Okay, so just a recap. So I have every edge is associated with the weight Wijl, where L is the layer index, and it's from 1 till capital L. So the output layer is capital L. The input layer, the first hidden layer, is 1. I have I input index. It's from 0 till D of L minus 1. So it comes from the input of the previous layer, the dimensions of the previous layer. And 0 is for the threshold. And then you have J, the output index, and it's from 1 till dimensions of the output layer. Okay. And we said, right, xj of L, so every, basically, the output or the activation of a neuron is the input to the next layer. So xj of L is nothing but a theta of the signal of J for this neuron J of L. Yeah, so basically the output of the input or the activation of a neuron is the some nonlinearity over the signal of this neuron that is getting to this neuron. And theta is not, and the signal is nothing but summation of weight times the input. Yeah, so if I go back here, I have here on this blue point, I have weight times feature, weight times feature, weight times feature, weight times feature, summation. That becomes the signal for this neuron. It passes through some nonlinearity, and that gives me the activation or the input to the next layer. Okay. I didn't understand it, but it has something to do with Labna and stuff, so I think it's not for us.
Yeah, I was sending it privately, but I sent it by mistake.
Okay, good. Bye. So what is theta? It's a nonlinearity, and we're gonna play with tan h right now, and then we're gonna change this in the next set of slides. So tan h is nothing but this formula. It's e to the power of s minus e to the power of minus s over e to the power of s plus e to the power of minus s. So it takes a signal, which is a real value, and it squashes it into the values between -1 and +1. So if you see, if s is very positive, it becomes +1. If s is very negative, it's -1. And in between, it's similar to a linear. It's close to a linear function. So it almost outputs the value of the signal when it's not very large or very small. Okay? We've seen something similar, which is when we're doing logistic regression, we've seen the sigmoid function, but it was squashing the signal between 0 and 1. Here it's squashing the signal between -1 and +1. Okay, so how does the neural network work? Let's assume I initialize these weights randomly. So all the weights on these edges are initialized to random values. All I have to do is apply the input. So the input, we refer to it as x0 of 0, x1 of 0, so of layer 0. So layer 0 is the input, then multiplied by the values of the current weights. That gives me signals over the neurons, passed it through the nonlinearity. That gives me the activations, which are the input to the next layer. So I get some inputs here, x0 of 1, x1 of 1, x2 of 1, and x3 of 1. These get multiplied by the weights of these edges of this layer. That gives me the signal here, s1 of 2. That gets passed through the nonlinearity to give me x1 of 2, and so on. Okay, so I apply the input, right, to the next layer and to the next layer and to the next layer. Finally, I get the output, which is the prediction h of x is equal to x1 of l. Yeah, so here at the output layer, I get x1 of l, right, where l is the number of hidden layers. So here I have two hidden layers, so I get x1 of 2. I have, sorry, 1, 2, 3 hidden layers, so x1 of 3, which is the hypothesis. Okay? Good. So now, how do I get the weights? So using some algorithm called backpropagation. Okay. So the hypothesis, the final prediction, is determined by all the weights W. Yeah, because I start with the input, multiplied by the weights, sum, and then pass through the neurons, and then do the same over and over until I get to the final layer, right, and output something. So it's determined by all the weights Wij of L. I need to get these weights. To compute the weights, I'm going to use stochastic gradient descent. Like the same thing we did in logistic regression. In logistic regression, we had only one neuron. Here we have multiple neurons, so it's more complicated. So what is stochastic gradient descent? The idea of it being stochastic is that I'm looking at a single example, not looking at the whole training set. Okay, so I have an error on example, I'll call it xn, and it's labeled yn. I'm going to refer to it as E of the prediction, right, and the label. It's a function of the prediction, what I predict given the current weights, and the actual label. And I'm going to refer to this as E of W. So that's error of the current weights. To implement stochastic gradient descent, I need the gradient. Yeah, so I update the weight as the old weight minus eta times the gradient. That's how I update the weights. And eta is just the learning rate. So it's the step I take along the steepest slope. Okay. So I need to compute the gradient of EW with respect to what? With respect to every weight that I have. So I must compute partial derivatives of the error with respect to every weight that I have in the network, Wij of L, for all I, J, and H. For every H, yeah, I have a gradient. And that's what how I update the weight on this edge based on this gradient. Okay, so let's see how do I compute the partial derivative of the error with respect to a particular weight Wij of L. So we evaluated one by one. Yeah, so we're not gonna update the weights in a vector form. We're gonna update it in one by one, or at least our calculation or our derivation is gonna be based on one by one weight. So we're gonna do what? We're gonna apply the chain rule. So delta of or the partial derivative of the error with respect to a particular weight ij of L is equal to the partial derivative of the error with respect to the signal, yeah, that this weight feeds into, times the partial derivative of the signal with respect to the weight. So I broke the error, the derivative of the error with respect to the weight. So the error comes from outside, from the very upper layer. And I want to get the derivative of the weight with respect to this particular weight I, Wij of well, any layer. So some layer inside the neural network. Okay, so I'm going to break it into derivative of the error with respect to the signal here times the derivative of the signal with respect to the weight. Okay, let's start with the derivative of the signal with respect to the weight. It's easier. So what is the derivative of the signal with respect to the weight? I know the signal. What is the formula for the signal? It's summation over all the weights coming from all the edges here, feeding into this neuron, times the input from on these edges, yeah, which is xi of L minus 1. For this edge, it's xi of L minus 1. For the other edge, it's going to be x, different I of L minus 1. So from the previous layer, it's input from the previous layer. Okay. So summation of, right, xi's times weights. I'm differentiating with respect to a particular weight only. So all the other weights become 0 when I do differentiation, and I get only xi of L minus 1. Yeah, the other weights here are multiplied by, edges here are multiplied by a different weight. So when I do differentiation, it goes away. Okay, so I get the partial derivative of Sj of L by Wij of L is equal to xi of L minus 1. Okay, clear? Good. The other component, so we basically need only this partial derivative of the error with respect to Sj of L. Note that xi of L minus 1 is something that I've already computed, given the current weights. It's nothing but, right, the activation of this neuron, which depends on the weights from the previous layer times the input from the previous layer. So I've already computed this value. So it's something that is known. The only unknown here right now to get the gradient is the differentiation of the error function with respect to the signal. Okay, so we're gonna call this delta J of L, where delta is an error. Yeah, so you can assume that this is an error or a gradient. Okay, so we're gonna call, so for every neuron, there is a signal, which is what feeds into the neuron, and there is an error, yeah, or delta J of L, a gradient, yeah, for this neuron. Okay, which happens to be the gradient of the error with respect to the signal at this neuron. Okay, good. We need to compute these delta J's. So we're going to start by the final layer, and that's how it works in practice. So you really, it's called backpropagation because you backpropagate these deltas from the final layer to the input layer. In contrast to how I compute the signals or the activations, right? The activations start from the input layer, and I forward propagate, the signal, and the backpropagation part, I backpropagate the gradient, this deltas. Okay, so I start from the final layer and backpropagate it. So let's see what it means. Delta J of L is for the final layer is equal to the partial derivative of the error with respect to the signal at the final layer. Okay, so the final layer, L is equal to capital L, and J is equal to 1 because we're assuming we only have one neuron in the outer layer. Yeah, so if you look at the neural network, the final layer has only one neuron, yeah, and so I have basically J is equal to 1. Yeah, and I'm gonna compute the delta here, the delta of this neuron at this area, which is basically delta 1 of capital. Okay.
So is it always one on the outer layer, or could it be more?
So we're gonna extend this to multiple neurons later on. So if you're doing binary classification or if you're doing regression, it's one neuron. But if you're doing multi-class classification, we'll generalize this to multiple neurons. Yeah, we'll talk about this in the next set of slides. Okay.
Okay, thank you.
You're welcome. Okay, so for the final layer, our L is capital L and J is equal to 1. So I want to compute delta 1 of L, the gradient of, at this final neuron, output neuron, which is equal to the partial derivative of the error with respect to the signal at this neuron. So we're going to consider regression, so squared error, but later on we'll generalize this to other types of errors. So assuming we're using the neural network for a regression problem and we have squared error. Yeah, so we're using the squared error to compute the error. So the error EW is equal to what? Is equal to what is the output? What is the prediction, which is x1 of L? Yeah, remember that that's the activation of the final neuron, the output neuron. It's x1 of the layer L, capital L, minus yn, the actual label, all squared. That's the error of the current weights. Yeah, the overall error of the current weights. Okay, so we're gonna differentiate this with respect to S1 of L. What is x1 of L? It's theta of S1 of L. So if I go back to the network, I have here basically S1 of capital L. I have here x1 of capital L, where x1 of capital L is nothing but theta of S1 of capital L. And the error is what? Is basically x1 of capital L minus the y all squared. Okay. So I'm going to apply chain rule again. The error of, or the derivative of the error with respect to S1 of L is nothing but the derivative of the error with respect to x1 of L times the derivative of x1 of L times by S1 of L. So I applied the chain rule. Yeah. Why I applied the chain rule? Because the error depends on x1 of L, where x1 of L is a function of S1 of L. So I can apply the chain rule, and that will allow me to differentiate. Okay, so let's do the first part. This is the error, x1 of L minus yn all squared. If I differentiate this with respect to x1 of L, what do I get?
2x1 of L?
2 times x1 of L minus yn.
Plus 2 minus 1 yn.
2 and then x1 of L minus yn, and then differentiation of what is inside the bracket, that's 1 with respect to x1 of L. So I get 2 x1 of L minus yn. And now what is the partial derivative of x1 of L with respect to S1 of L? It's theta dash of S1 of L. Theta dash is the derivative of theta. Yeah, so x1 of L is a function of S1 of L. So basically it's just the derivative of theta with respect to S1 of L. Okay, given that we have theta is tan H, we know that theta dash of S is 1 minus theta square of S. You can verify this using the formula. The formula is E of S minus E of minus S over E of S plus E of minus S. If you do the derivative of this, you get, with respect to S, you get that theta dash of S is equal to 1 minus theta square of S. Okay? Good. So now I can compute delta 1 of capital L. It's nothing but 2 x1 of L I already computed. It's my prediction given the current weights minus the label of the point that I'm looking at because I'm doing stochastic gradient descent. So I have this value, and I have theta dash of S1 of L is 1 minus theta square of S1 of L, of course. Yeah, so it's going to be 1 minus theta square S1 of L. And I know S1 of L given the current weights. I've already computed the signal for the output neuron. So I have this value. I have delta 1 of L. It's some number. Yeah. Now I'm going to back propagate it to the previous layers. Okay, so let's see the back propagation. So I want to compute delta I of L minus 1 for any neuron. Remember, for any neuron that I have in the network, there is a signal here and there is a gradient, right? This delta I of L minus 1, sometimes referred to as R as well. Yeah, so basically error at this point for this neuron. Yeah, it's delta I of L minus 1, given that this is the signal Si of L minus 1. Okay. So I want to back propagate the error from the layer L to the layer L minus 1. Okay. Like I do signal from layer L minus 1 to layer L. I do the opposite, right? Back propagate the delta from layer L to layer L minus 1. Okay. So what is delta I of L minus 1? It's the partial derivative of the error, the outside error, the real error, complete error, with respect to the signal at this neuron. Yeah? So it's partial derivative of error of W by Si of L minus 1, where Si of L minus 1 is the signal at this neuron. Okay. So what is this? Again, I apply the chain rule. So it's the partial derivative of the error W with respect to the signal at Sj of L. Okay, so basically, I want to compute the partial derivative of the error with respect to the signal. So I'm going to compute it through the signal first, and then do some chain rule to get it to the Si of L minus 1. So it's partial derivative of the error with respect to Sj of L, where Sj of L is the signal at the neurons in this layer, times the partial derivative of the signal with respect to Xi of L minus 1. So this by this, times the partial derivative of the Xi of L minus 1 by Si of L minus 1. Okay, now I have summation here because, right, this neuron feeds in all of these neurons. So I have to do summation over all of them. Yeah, the error is back propagated from here, or the delta is back propagated from here, but also back propagated from here, back propagated from here. So there are multiple deltas that are back propagated into this neuron. Like we did in the forward pass. In the forward pass, I had, multiple edges contributing to the signal here. In the backward path, I have multiple deltas, right, contributing to the delta. Yeah, so you can always view it as similar to how we do the forward pass. Okay. So what is this guy? Delta, a partial derivative of EW by Sj of L. That's delta J of L. That's what we call delta J of L. So if I already computed this, then I know it already. Yeah, and I've already computed it for the output layer, and I can back propagate it to the previous layer. Okay, let's see the second component. The second component is the signal here, partial derivative of the signal here with respect to this input, Xi of L minus 1. What is this? This is basically Wi of J. Wij of L. Why? Because all the other ones, you want to do the signal. The signal is summation of weights times W's. But the only one that depends on Xi of L is Wij of L. Yeah, so I get Wij of L. And then I have this final part, Xi of L minus 1, the derivative of this with respect to the signal. And that's nothing but theta dash of the signal. Because why? Because Xi of L minus 1 is theta of Si of L minus 1. Okay. I know what is theta dash of Si of L minus 1. It's 1 minus theta of Si of L minus 1.
So can you repeat the weight? From where did the weight come from?
Yeah, okay. So basically, I have here, I'm doing the second part, the derivative of the signal with respect to Xi of L minus 1. Right? Remember that the signal here is equal to what? Is equal to Wij of L times Xi of L minus 1 plus the other, right, weight times xi's coming from the other neurons. Okay, all of these go away because I'm differentiating with respect to one particular activation, xi of L minus 1. So I get only wij of L, right? Clear?
Okay. Thank you.
You're welcome. Okay, so I get this, three things multiplied by each other. Theta dash of Si of L minus 1 is basically nothing but 1 minus theta of Si of L minus 1 squared. We've shown this in the previous slide. And that's 1 minus Xi of L minus 1 all squared, because Xi of L minus 1 is theta of Si of L minus 1. So I get this outside the summation. It doesn't depend on J. And I have summation from J equal 1 to GL. So all in this layer, right, the neurons in this layer, Wij of L times the gradient at this neurons. So it's very nice. It's similar to the forward pass. If you look at it, it's very similar to the forward pass. In the backward pass, or in back propagation, I multiply the weight by the value of the gradient here, or the delta, and then sum. So multiply the weight by the value of the gradient here and sum. Where, right, these edges are the ones that I feed into. So basically I feed into. That gives me the gradient at the previous layer. Just don't forget to multiply it by 1 minus Xi of L minus 1 squared. Yeah. This is all. The details of this is not very important. I just get the gist of it, the intuition behind backpropagation. So there is a forward pass and there is a backward pass. The backward pass, all it does is backpropagates the error. Yeah, so it backpropagates the error by multiplying it by the weights and summing, and then doing some additional multiplication of the activation. Okay, so here's the algorithm. You're not going to implement this algorithm from scratch, but you need to be able to understand it, because this is the core of neural networks. So if you're training a neural network, you will see that this is the algorithm used, and you need to be able to understand how it works, yeah, so that you can optimize it and train a neural network on your data. So the algorithm starts by the following. I initialize all the weights, Wij of L, at random. And we'll talk about why at random in a bit. And then I shuffle the training set to add some randomization, so that, right, I don't, because I'm doing stochastic gradient this time. And then I repeat. So I have two loops. An outer loop that runs indefinitely, and an inner loop that runs over the training examples. So from n equal 1 till capital N. Forward pass, I compute all activations xj of L. How do I compute these guys? Feature values times weights, sum, that gives me signals, pass it through some non-linearity like tan H, that gives me activation of the next layer. Multiply these activations by the weights of the current layer, sum, that gives me signals, pass it through non-linearity, and so on, until I get to the output layer. So I compute all the activations at all the neurons that I have. Okay, that gives me the output. I can compute the output minus the label. That gives me the error at the output layer, and then backpropagate this error. So backpropagate the error. We've seen how do I backpropagate it. Multiply the weight by the gradients, deltas, and sum, and then multiply by 1 minus the activation squared. Okay, and finally update the weights. So I update the weights, the old weight minus the learning rate times xi of L minus 1 delta j of L. Where did we get this from? We got it from here. Right, from here. We know that the error, the gradient of the error with respect to Wij of L is nothing but xi of L minus 1 times delta j of X. If I computed this and I computed this, the current weight should be updated by updating it minus the learning rate times this times this. Okay.
So the meeting is about to end in 4 minutes. Let's all leave and then come back, log in again.
Okay. Let me finish this one more slide, and then we'll end it. Yeah. Let me finish this. I have a couple of slides very fast, so we'll finish it before the meeting ends. Okay, so I update the weight based on gradient descent. And then I take another example, update the weights based on it, all the weights in the network based on this example, and so on until I do one epoch over the whole data set. One epoch means I pass through the whole data set. All right, so now I have updated the weights. I repeat this multiple epochs, so I run multiple passes over the whole data set until fixed number of iterations or until the error doesn't change anymore, and then return these final weights as the final neural network weights. Once I have these, I can now use them to predict for any input by just passing the input through the different layers. Yeah, so multiply by the weights, sum, pass this through nonlinearities over all the neurons, and repeat this for the next layer and so on until I get the final prediction. Okay, summary of neural networks. The hidden layers, right, learn nonlinear transforms. So it's very powerful because why are neural networks very powerful? Because they are similar to nonlinear transformations. Yeah, because I'm getting signals. Yeah, so weights times features, and that's linear model. But then I pass it through some nonlinearity, and that gives me as if I'm doing nonlinear transformation of the input. It's unfortunately very hard to comprehend or understand. So I don't understand what are these features. Yeah, so the things that I'm learning here. So every activation of a neuron represents a new feature, but I don't understand what is this feature. So it's a combination of previous features in a non-linear form, but it's not really comprehensible. So I can't understand that this is, you know, something meaningful. A meaningful representation of the features. Yeah, so that's the downside of it. Okay, I'll stop here and then we'll stop the meeting and resume in a second. Okay. Mm-hmm.